In the previous lecture, we are talking about the Monge's cone. So for that, we are discussing the Cauchy problem for nonlinear first order PD. So the expression for the first order PD is defined as f of x, y, z, pq equal to 0. And f, here f is a continuous second order derivative function with the function of x, y, z, p and q. Then the Monge's cone can be written in the form of q of x0, y0, z0, p, where x0, y0, z0 is a vertex of that cone. The second equation is z minus z0 is equal to p into x minus x0 plus q into y minus y0. This is the equation of the plane. And the equation of the line is called generator line is x minus x0 is equal to y minus y0 upon fq. We call it, this is the equation number 6. Whatever the equation number is, we have defined in the previous lecture. We will continue with that equation number. And we have solved one examples based on this to find out the Monge's cone for some equation, that is p square plus q square equal to 1. Now here we should note that a quasi-linear equation, the quasi-linear equation that is capital P into small p, q into small q is equal to r, where every tangent plane that is z minus z0 is equal to p x minus x0 plus q into y minus y0. This was the tangent plane that we have. Contains the following line. Contains the following line, that is x minus x0 upon p is equal to y minus y0 upon q is equal to z minus z0 upon r. This is a direction line and this is a tangent plane, and this PQR is in the direction of the normal, direction of the tangent, and this x0 y0 z0 is the vertex, which is point. So that's why this is a line will satisfy. Hence the Monge's cone is generated by this straight line at each and every point. So what we can say is, hence the Monge cone is degenerate into the above straight line. At each point. Now let us find out the equation of the characteristic curve. So what is our objective is to find the equation of characteristic curve. This will do here. As the line of contact between the tangent plane and to the solution surface, or I can say integral surface, and the Monge's cone at the point is generator of that Monge's cone. So the intersection of the tangent plane, a solution surface, and the Monge's cone is the generator of Monge cone. So we'll write that as a line of contact between the tangent plane to an integral surface and Monge cone at that point is the generator of the Monge cone. And it can be written from the equation number 6 which we have says as what was the equation number 6 that we have written in this form. It is x minus x0 upon fp y minus y0 upon fq is equal to z minus z0. So you can just see that it is equal to k. Let me write that first. So it is x minus x0 upon fp y minus y0 upon fq. Then it is equal to, using this, if I can say this is equal to k, then x minus x0 upon fp. So what will we get here? If I can say this is equal to k, then x minus x0 equal to kfp. Y minus y0 is equal to kfq. If I substitute this x minus x0 and y minus y0 into this equation, then z minus z0 is equal to kfp plus qfq. K is common. So that means the value of k will have z minus z0 upon p into fp plus q into fq. And that value of k, if I substitute here, then we'll get that here it is z minus z0 upon p into fp plus q into fq. Hence the characteristic direction which is lying along the generator into this direction. This is the direction, that is fp, fq is the direction of the characteristic curve, or I can say it is a characteristic direction. So hence the characteristic direction which lies along the generator of the Monge's cone are given by fq, fp, pfp plus qfq. So this is the direction of the characteristic direction. So hence the characteristic curves are the solution of the characteristic curves They are the solution of dx upon fp. This is I have written wrong. This is fp and this is fq. fp, this is fq. So dx upon fp, dy upon fq, and dz upon pfp plus q fq. So if I can say this is equal to dt, then we'll have dx upon dt equal to fp. So dx upon dt is equal to fp. dy upon dt is equal to fq, and dz upon dt is equal to pfp plus qfq. So this three ordinary differential equation will get, and the solution of this three ordinary differential equation determine the characteristic curve, and it cannot be solved because they are involved p and q, and so we required a more information regarding the variation, what will be the value of p and q, and for that we need to have some information regarding the characteristic curves which involves p and q, and along such curves we given integral surface will define something else. So let us write down what I said just now. Since this three ordinary differential equations for determining the characteristic curve, so that determine the characteristic curve x of t, y of t, z of t cannot be solved due to, because they involve the function p and q, and what we required is more information regarding the variation of p and q along the curve, characteristic curve. Characteristic I have written in the short form CHAR, characteristic curve. So along such curves on the given surface, what will be dp by dt we can write down. So we have a p which is a function of xy, and x and y are the function of t. So here p is a function of x and y, and x and y are the function of t we have. So we can talk about the total derivative of p with respect to t. So that will gives me del p by del x into dx by dt plus del p by del y into dy by dt. So del p by del x we can say it is px. Dx by dt we already obtained it from here, that is dx by dt is fp. So that's why it is fp plus this is I can say py, and dy by dt we already obtained it is fq. Same way dq by dt will say it is dp by dx, not p but it is q. dq by dx into dx by dt plus dq by dy into dy by dt. So this I can write down as qx, this is fp, plus qy fq. We'll call it, this is, we call some numbers here. So we'll call this as equation number 7. This equation we have written it is 8, and this one, the last one which we got, both this one and this one, both that equation as 9. Now on differentiating equation, that is f of x y z pq equal to 0 with respect to x as well as y, we get it. So we have to differentiate this equation with respect to x and y. So actually this function is a function of x, y, z, p and q, where y and z are independent, but p and q are the function of x. So when I differentiate this with respect to x, we'll have del f upon del x plus into dx by dt, but dx by dx is 1. For this two, it will be 0. We'll have del f upon del p into dp by, not d, but del p by del x plus del f upon del q into del q by del x is equal to 0. And del f upon del y will differentiate with respect to y, will have y whenever we have x. So this is the things we got. If I can call this is a equation number, nothing, no required of this, but afterwards we can have. Now what is px? You just observe px is, what is p? It is del z by del x. So actually I don't want px, but I want py. I want py. What is py? It is del square z by del x del y. And what is qx? We know that q is del z by del y. Qx, that is del square z by del y del x. But z is such function where this mixed partial derivatives are equal. So we should note here py is equal to qx. These things we have. And if we use that one into the above equation that is here, then this equation can be written as fx. The first value can be written in the fx. This is px. And this one is qx. So what we can write from this, it is fx plus fp into px plus fq into qx, but qx is py, so instead of that we'll write down py here is equal to 0. So this first equation can be written in this form. Second equation, that is fy plus fp, then it is py, but py is qx, so I just write down qx here, plus fq qy equal to 0. And you just observe what is the equation number 9 we have. It is px fp py fq. So it is px fp px fp py fq, px fp py fq. So that will gives me px fp py fq is equal to minus fx, and this will gives me, just say, see the equation number 9, qx fp. So that is qx fp plus qy fq is equal to minus fy minus fy. And if I use this value into the equation number 9, so using above values, in equation 9 we get dp by dt is equal to, just observe that equation 9 is this, so it will gives me, oh, here I make a mistake. Oh, shit. Yeah, so here we are differentiating this with respect to x and y. Z is also depends on x and y, that we have not considered here. So it is del f by del x. So what is the things we got here? It is del f by del x plus del f by del z into del z by del x. This quantity is left. Here is also del f by del x, del y plus del f by del z into del z by del y. So as per this, we'll get here, it is plus, instead of fx fy, we'll have fx plus fz zx, fy plus fz zy. So here we'll get pfp pfq is equal to minus fx minus we'll have minus fx minus fz zx. Here we'll get minus fy minus fz zy. So that's why here we'll get dp by dx using the equation number 9. That is this. If I put this value as this, watch, it will gives me minus fx minus fz zx, but zx is exactly the value of p, that is del z by del x, which is zx. So that's why it is minus fx minus p fz, and dq by dt will be minus Fy minus Fz Zy. But the value of Q is del Z by del Y. So that's why this will be minus Fy minus Q into Fz. So thus what we got, we'll call this as equation number 10. This Z is equal to f of xy is the integral surface which corresponds the family of the curves surface associated with the coordinate. So that means now we have a 6 equation. Altogether there are 7 equations. No, 6 equations. So in order to determine the integral surface using the discussion that we are doing is to actually calculate or to find out a solution for 6 ordinary differential equations. So in order to determine the integral surface by the previous discussion, we consider the p.d.f of xyz eq equal to 0 along with the system of characteristic equation, that is the characteristic equation that we have taken is the 6th equation, that is f of xy z eq equal to 0, that is the first equation. Dx by dt that we got from the equation number 8, it is fp. Dy by dt it is fq. Dz by dt it is pfp plus qfq. The other two we have just now we have got dp by dt is minus fx minus pfz, and dq by dt is equal to minus fy minus qfz. It is exactly this sides on the right hand side of this all equation, which is the same as the Charpit's method we got, dx upon fp, dy upon fq, dz upon pfp plus qfq, dp upon this and dq upon this. That is exactly the same expression that we got. And there are 5 unknowns. What are that unknowns? X, y, z, p and q. Okay, and there are 6 equations. And thus this system is not overdetermined. So consider the solution of 5 equations. So whatever the solutions we got, so we'll say it is for the 5 unknowns functions x of t, y of t, z of t, p of t and q of t. This system is not overdetermined. Consider a solution of the last 5 equations. So that means whatever the differential equations we have of, if I can call all these equations as equation number 11. equation of 11. Yes, what is happened? Along the solutions, we can also find the surface of the curve, that is along the solution we can find that what is df by dt. That means f is function of x, y, z, p and q, and all of them are function of t. So that's why it is df by dt will be del f by del x into dx by dt plus del f by del y into dy by dt plus del f by del z into dz by dt plus del f by del p into dp by dt plus del f by del q into dq by dt. So this f is a function of all these variables, and so that's why this will be this. So it is fx dx by dt. From the equation number 11 we have fp, so that's why it is fp plus fy into fq plus fz into pfp plus qfq plus fp into dp by dt. dp by dt we have calculated is minus fx minus pfz plus fq into minus fy minus qfz. And just observe that every term here it is cancelling out. Let us see that. So we'll get df by dt is equal to fx fp plus fy fq plus p into f z fp plus q into fz fq. That you can see that this fz is multiplied to both. Now fp minus, instead of plus we have minus, we'll have fx fp minus pfz fp pfz fp. Then it is fq minus fy into q qfz fq. You just see that everything is cancelling out and we'll get 0. So hence what we get, the derivative is 0. That means the function f is constant and is the integral surface, integral of system of ordinary differential equation. Okay, and thus we can conclude that the equation, thus the equation f of x, y, z q equal to 0 is not much of restriction. Suppose that f equal to 0 at point x0, y0, z0, p0, q0 at point t equal to 0, then the unique solution is possible. Solution of characteristic equations passing through this point is such that f equal to 0 will be satisfied for all t along the solution. Why? Because this is gives you f equal to constant, and f equal to constant, if you change the value of this constant, it will have a different solution. But now we'll suppose that at initial point f is 0, then the solution will be 0. That means f is 0, and that will satisfy all the conditions of that. And now we'll give the definition of the characteristic strip. A solution x of t, y of t, z of t, p of t, q of t of system of ordinary differential equations, that is 11, can be intercept interact as a strip. The first three equations that we have here, the first three equations, or first three functions, that is x of t, y of t, z of t, determine the space curve. And each point of the space curve, at each point, of the space curve, p of t and q of t define a tangent plane with pq minus 1 as a normal vector. And the curve along with this tangent planes, at each point it's called the characteristic strip. And the curve along with this tangents planes, at each point it's called characteristic strip. And the curve, it's called the characteristic curve. So the situation is like this. You have one plane is here, Another plane is at this point you have one plane, another plane is here, and all these planes together. So this is the situation together with forms one curve, and this strip is known as characteristic strip. Every point has different plane, tangent planes, and using that tangent planes we can characterize this characteristic strip. For fixed point P given by T0, x0, y0, z0, p0, q0 is said to be an element of the strip. So whatever the you value fix the value of t, then it will be an element of. That means the point x0, y0, z0 on the curve and the corresponding tangent plane whose normal is given by p0, q0 minus 1 at that point. Now any point, any five function x of t, y of t, z of t, p of t, q of t can be interested in a strip only if the following condition satisfies, that is dz by dt is equal to p of t dx by dt plus q of t dy by dt is satisfies. This condition that each point on the space is the tangent to the curve lies on the plane whose normal has a direction ratio of q equal to minus 1. Then there is a one lemma is there. We'll not discussing the proof of that lemma, but let us see what is the statement. If an element x0, y0, z0, q0 is common to both an integral surface z is equal to z of xy and characteristic strip, then corresponding characteristic curves lies on the integral surface. So we'll not discussing the proof of this. Okay, what is this statement says is the common. So whatever the element which is common in both integral surface as well as the characteristic strip, then corresponding characteristic curves is also lies on the same curve or same integral surface. And we'll use this lemma to prove the uniqueness of a solution of Cauchy's problem for nonlinear partial differential equation. So this lemma is used to prove a uniqueness of solution of partial differential equation, and that we will discuss later on. But before that, let us solve certain examples to find out a Cauchy's problem for nonlinear differential equation.